Hello, my name is Gabriel Cooper, and my presentation is on the nuts and bolts of deploying a process level IDS in industrial control systems. First, I want to go over some acknowledgments with the authors. The first author is Magnus Algren, Wilson Audi, Robert Gustafsson, all three from the Chalmers University of Technology. We have Robin Kral from the University of Freiburg and Andreas Lindhe from Combitech. Here's an overview of what I'll be talking about today. I'll start with the introduction, talking about what the paper is about and what the authors are trying to do. Then I'll discuss the challenges that they have pointed out in the paper. Then we'll talk about the system design and what they impose on trying to deploy. We'll talk about the hardware that they chose. And then we will first go over the controlled experiment before that they did in a university. Then we'll talk about the live experiment they've done at a factory. Then we'll discuss with the discussions that they presented and the results that they found, and we will finish up with the lessons learned. Industrial control systems monitor and operate industrial processes. Some of these include manufacturing, gas, power distribution, and transportation. Increasing connectivity of ICS renders these systems it's eventually vulnerable to different cyber attacks. Some of these are capable of doing damage to essential infrastructure. The authors had done some research on some of the possible ways to detect these type of attacks. I've listed some examples, the Tennessee Eastman process, and they also did some research in the SWAT testbed. However, the authors feel that there was a lack of real-world experiments. There's a lot of things that they need in the real world that you won't have in a simulated test bed. And they felt that was very important to try to have some kind of experiment in a real environment. So the authors proposed and have ran through a test of an IDS built from the ground up, and they deployed into a paper factory for 75 days. And at the end, they highlight some of the results that they found and include some recommendations moving forward for future researchers and those who plan to do a real solution. Here are some of the main challenges that were highlighted in the paper. Some of these was the unknown environment, performance footprint, system stability, and trust in data access. And we'll go deeper into these specifics of what the authors were describing these challenges. So first is the unknown environment. So ICSs are complex, mainly composed of proprietary software and hardware. And these itself can cause some challenges itself that some models and specifications will vary between machine to machine. And so there is lack of consistency between when you come from different factories. And due to this expected lack of knowledge and processes, the authors determined that data-driven methods are better over specific-based methods. However, the drawback in the decision, the authors, it's non-trivial to decide what to monitor, or what machines, what sensors to focus on. So some factories are covered with sensors and covered with machines, and there needs to be a operational technology knowledge prior to deployment of these systems in order to figure out which machines or which sensors to focus on. And also, the training window is can be difficult to specify how long it should be good, like what should be a good time to train. In the paper, the authors do an 8-day training for their experiment, and they find out later in the paper that even 8 days was not enough to get a good baseline. Performance and footprint. The authors describe the importance of achieving high memory efficiency to have the IDS be able to utilize memory efficiently. And because in ICSs, you'll be working on limited resource hardware. Some of the PLCs don't have much resources to spare, and it's very important that the IDS can run efficiently. There's several reasons for this also, but for cost, scale of deployment, and also the types of machines that are available in ICSs to deploy on. All of these things kind of matter when you're developing the IDS. There's also that IDS needs to be able to make real time decisions. So it needs to be able to not only keep memory efficient, but also be able to operate quickly enough to make those decisions in time to respond to an attack. So balancing between the two makes this quite the challenge. And there's system stability. While keeping in mind that we're trying to run on cheap hardware, the IDS also needs to be able to be stable to handle sudden crashes, lack of information, lack of sensor data, packet loss, or even corruption, memory management. And so, when developing the ICS, it is very important to include logging, a logging mechanism, a logging management to be able to look back and troubleshoot some of the issues that happen while deployed in ICS. The authors also wanted to prevent having to put more burden on the IC staff, and so they implemented an automation of handling the incidents, and that way that the staff is not sitting there having to learn the IDS and having to manage it themselves. It is all automated. Trust and data access, the authors actually find it very difficult to actually get data from the factory onto the university, and found it actually very much easier to just do a lot of the training on site instead. And so this can contribute to a lack of online access, lack of trying to pipe it back to the university. And so a lot of times things had to be backed up locally, um, so that and by the ICS staff and brought back to the university. And that itself causes a lot of issues, as the staff needs to have knowledge on how to run a network dump or how to set up a mirror port. And these are things that they may or may not have this kind of knowledge. And so this causes a challenge in itself to run the IDS. So now we will move to the system design. The total system that the authors propose is composed of two main components: a process-aware stealthy attack detection mechanism, which is specification agnostic, and it operates at the process level. And well, also known as PASAD, it also needs to be able to be served network data. And so the authors has included a mechanism called MIDBRO, which is a packet capturing for intrusion detection systems. And let me go deeper into these details. So we will first talk about PASAD, and it is mainly composed of two phases: a learning phase and a detection phase. The learning phase is where it learns the normal behavior of the system, and this is done mathematically through analysis of historical data. The data is extracted using a singular spectrum analysis, where over a time series it builds out a vector space, where pretty much the different vectors, its normalized area for anything outside this area would be determined malicious. So just as long as any type of future acts or any type of behavior is within the subspace, it is considered to be normal behavior, and anything outside is malicious. Detection phase works with a sliding window where it will pipe in new activities, new events that's happening during the detection phase, and it will calculate whether or not it fits in the subspace that was developed during the training phase. And if it deviates far enough, if it drifts from normal behavior, it will act on it as it being malicious. During the detection phase, there is a threshold in which it allows for wiggle room. And just as long as it's under that threshold, it will pass as normal behavior. If it exceeds it, it is malicious. BRO is comprised of two subsystems: a network capturing engine called BRO, and a buffer mechanism designed by the authors. Midbro was actually it's a system created by Robert Gustafson, Robin Kral, and Andreas Leahy in 2017. Uh, its network capturing engine captures and processes network, and it stores and registers for it to be passed off into to PASAD. It is composed of three different layers. The libcats, which is responsible for capturing those packets off the network, an event engine, which parses the packets and generates new events, and a policy scripts, which triggers warnings and writes files and generates new events. These register values come for the event placed on the buffer and is held until the PASAD requests a new event. And this is where the buffer mechanism comes in. The authors decided to use a FIFO, and they realized earlier that they wanted to make sure that the buffer doesn't overfill. So they tried to use a relatively large buffer and have asynchronous operations to the buffer, where it's pushing on the top new events and on the tail end popping um, popping new events back to PASAD. And they do this to have new events be the first to be evaluated. In the case that where PASAD is too busy and doesn't get any new events for a while, instead of dropping old events, it wants to make sure it passes the relatively new ones. And so it does a head first policy where it drops off the oldest events. Um, since Midbro is single threaded, the authors implemented a two thread system where you have a producer thread and a listening thread. The producer thread is constantly listening to the socket where Bro events are sent. The sensor values extracted from those events are added to the tail of the queue. The consumer thread pops values from the queue and serves them to PASAD on request. And also, Midbro has a API, a it's a Bro client communication library actually, and this allows the communication between PASAD and Midbro, and so it's enabled by request and response API. With this technology communication, function calls are used to request a number of new sensor values. The authors did research to use the Raspberry Pi 3. This device is easily accessible and it's affordable, and it has a gigabit Ethernet with a high clock processor. And the authors believe that this is suitable for network analysis and to serve their needs. The Raspberry Pi also has a very active community and has lots of backing and documentation. So it should be relatively easy to look up troubleshooting, how to use, and is very suitable for widespread and scalability. The Raspberry Pi also comes with a pre-packaged Bro and Broccoli in its official repositories. Now let's move to the controlled experiment. So the authors done their controlled experiments in a local university lab, and the authors set up a host relays of previous recorded traffic. The traffic was specifically a water plant distribution. The network traffic in this controlled experiment consisted over 24 hosts and was ran over 164 days. The data originates from an HMI, which operators use to monitor the processes and issue commands to the different offices and different control processes. One notable distinction is that the authors found it very useful to run a locally controlled testbed before moving to the live. They were able to confirm that their system worked as intended, and they were able to test for a long longevity They were actually ran extra tests over a weekend untouched to make sure that no issues arose for running over 24 to 48-hour period. And also from the controlled experiment, they were able to throttle the data rate and cause simulated outages to ensure that the system could handle unexpected interruptions and be able to gracefully reboot or be able to handle lack of data coming into the buffer. The live experiment was done in a paper factory in Sweden. The authors were able to work with the staff to identify what machine to focus on and what sensors target. The sensor was placed on an ABB NP1 1200, which you can see on the right. The mod interface, the ABB I867, which is on the left, and the controller, which is in the middle, the ABB PM866. The authors connected their system via Ethernet to the switch, allowing the connection to the Modbus interface. This live experiment test was over 75 days without any intervention. And the only time the authors had to interfere with the system was to extract data to ensure stability and performance. All right, so the discussion and results, they got so a couple of figures, as you can see to the right. They observed that the system was very, very stable throughout the test. Um, in the blue, you can see that the 8 days of training that they were able to do to establish the normal behavior, and the black is the validation, the actual raw readings that they used for detection. On the bottom graph, you can see where they set the threshold slightly higher than the max spike, essentially the departure score from the vectors between the training and the actual detection vectors that is calculating. The There you can see in the long vertical red lines, those are actually it's the vertical the gaps in sensor readings. The authors were able to confirm with the facility of when there were scheduled outages for maintenance or scheduled outages for any type of operations needed. It corresponds with the graph of when their system went down. And so they observed that the system did gracefully handle interruptions. It was able to reboot on its own, and there was no intervention needed by the staff. This next graph shows some of the CPU usage and the memory usage. Uh, the authors found this very, very important as the CPU usage has to stay relatively low. The fear was that if the CPU usage was stayed very high over a long period of time, this can cause packet drops. And with packet drops, there will be events missed. This is an opportunity for things to slip by the system, and this is things that the idea is not wanted for the IDS. And the authors were very happy to see that the CPU usage stayed below 50% majority of the time. There were a very, very limited amount of time where it did spike up to 100%, but it wasn't concerned that for package drops. The memory usage was also stable. And so overall, the IDS handled very well during the period of time. So there were several lessons learned that the authors wanted to express. They wrote the lessons learned in a set of guidelines that they recommend for future researchers and for those who plan to develop a permanent solution. Some of the things they focused were process knowledge, signal data disruptions, and Modbus parsing and buffering. So, process knowledge, the authors learned from their tests in the real environment that Even though that the IDS is process agnostic, this is not a true plug and play. Um, some scenes will have multiple thousands of sensors alone, and even with that, just trying to determine which machine to even target in the entire factory is a very tall order. And so, it when deploying, there needs to be an operation technology and information technology personnel needed to just be able to identify the requirements of what machines or what sensors to even focus on. And this can add lots of complexity in the development and the deployment of the IDS. In this paper, though, the authors did have a lot of discussions with their contact from the factory and was able to settle on the single register they knew that was holding relevant data. Signal data disruptions, and the authors want to emphasize that when developing an IDS to make sure to account for long-lasting interruptions. One of the interruptions they experienced was over 18 hours due to maintenance. And though they had this foresight, their IDS was able to handle it gracefully. It is important for future IDSs to make sure they can address when there's a lack of data, when there's a lack of signal packets, and be able to handle it without the intervention of a user. They also find it difficult to distinguish between a crash process and an interruption of data. Um, in the author's case, they had automated their reboot process to happen every 30 minutes where there's no data being ingested. And so even though that there's a constant reboot happening, uh, there was very, very minimal need for any manual reboot, which after speaking with the ICS staff, this was much more favored. So the authors wants to make sure that to take this in consideration. Mode bus parsing. The authors actually were very pleased with the performance of Midbro. It was able to extract and capture packets very, very fast. There was no issues with the sensor data coming in too fast, as it never reached Midbro's threshold. However, that does not change the fact that Midbro is single threaded. This becomes an issue in the fact that Midbro needs to focus on this network, um, extracting packets from the network. And so they recommend that you minimize the work in Bro to be minimum, not to have it do extra tasks, and that it focus on passing that network data. And so in this example, with the paper, that they had a buffering mechanism that handled that two-threaded producer and consumer threads. Something along that that's outside of Bro is heavily, heavily recommended. One of the other possible substitutes for Midbro is Snort. The authors did not choose Snort because they found that writing in Snort would took a significant amount more time to write the code needed for their system. And Midbro, they found it relatively easy to write the code they needed. And so, even though that Snort is a wonderful technology to also implement in the system, they prefer to use Midbro. Also, they found that Midbro does not match the corresponding requests and responses for the Modbus protocol. And so the authors addressed this by inspecting the headers in the packets for the transaction ID, and it was able to do a match that way. But this is something definitely to consider when deploying an IDS. And also the buffering. The authors, as I mentioned earlier, they were able to use a much larger FIFO, and they heavily recommend the head drop policy, and just to ensure that the IDS is getting the most relevant events that come into the buffer, and is not passing up, it's not favoring old packets and old events over new ones. Otherwise, this can cause issues and miss events in the ICS. And this wraps up my presentation, and thank you so much for watching.